Hello everyone, my name is Ning from the University of Alberta. This is joint work with Bradley Hauer, David Basil, Zhang, and Greg Kondrak. We gratefully acknowledge the support of Uncerc and Amy. Today, I will present our work titled Word Surprisal Correlates with Sentential Contradiction in Large Language Models. Let's start. First, I would like to introduce what we mean by sentence-level contradiction. In natural language inference, a contradiction is defined as a relation between a premise and a hypothesis, such that the premise entails the negation of the hypothesis. Intuitively, this means that if the premise is true, then the hypothesis must be false. Let us look at a simple example. Suppose that the premise is John is in the bedroom, and the hypothesis is John is in the kitchen. We know if John is in the bedroom, then he cannot be in the kitchen at the same time. So the premise entails the negation of the hypothesis that John is not in the kitchen. So this results in a contradiction. This is standard formulation of contradiction used in LI, and it provides the semantic foundation for our work. What is a word-level surprisal? Surprisal tells us how unexpected a word is given a context. Formally, it can be defined as the negative log of the conditional probability of a word given the context comes before it. In simple terms, if a word has low probability in that context, it has high surprisal, and high surprisal means the model did not strongly expect that the word to appear next. Let's look at a simple example as well. Suppose the context is the capital of Canada is. If the next word is Ottawa, the surprisal is low, because it is the correct and highly expected answer. But if the next word is Edmonton, the surprisal should be higher, because it is less expected in that specific sentence. So, surprisal gives us a clear signal of how much a word goes against the model's expectations. In this work, we studied the relationship between word-level surprisal and sentence-level contradiction. More specifically, we ask a simple but important question: how does a language model respond to semantic inconsistency between two given sentences? In other words, when the model reads a hypothesis that conflicts with the premise, do the content words in that hypothesis become more surprising? We put forward that when a hypothesis is conditioned on a premise, the surprisal magnitude of content word in that hypothesis is positively correlated with the presence of a contradiction. If this is true, it gives us a clear link between word-level probability and sentence-level reasoning. The rest of the talk is about testing this idea carefully from a theoretical point of view and through extensive experiment. To answer our research question, we bridge lexical uncertainty and sentential semantics through both theory and empirical analysis. First, we provide the first systematic study of the link between word-level surprisal and sentence-level contradiction in large language models. Surprisal has been studied in psycholinguistics, and the contradiction has been studied in LI, but no previous work has directly connected these two at scale. We make that connection in a clear and quantitative way. Second, we introduce a token-to-word decoding algorithm. Modern large language models most work with subword tokens, not words, so computing accurate word-level surprisal is not straightforward. Our algorithm allows us to recover reliable word probability, even in open vocabulary settings. That technical step is what makes our study possible. Third, we run extensive experiments across multiple datasets and different model families. We consistently observe a positive correlation between surprisal and contradiction. The results are statistically significant and generalized across domains. Together, these contributions build a concrete bridge between word-level probability and sentence-level reasoning in large language models. To test our assumption, we design our method along three main dimensions. First, we change how we present the premise and the hypothesis to the model. This directly affects what the model conditions on. In the edge-only setting, the model sees only the hypothesis. This allows us to understand its internal expectations without premise information. In the cat setting, we simply put the premise and the hypothesis together, so the hypothesis is directly conditioned on the premise. In the temp setting, we place them in a causal template, such as since the premise, therefore the hypothesis. This encourages the model to treat the premise as supporting the hypothesis. Second, we change how we compute surprisal. The direct surprisal follows the standard definition. The relative surprisal adjusts by comparing the word probability to the most likely next word, which helps when overall probabilities are low. Third, we change how we combine word-level surprisal values into a single sentence-level score. Since a hypothesis has multiple content words, we test three simple strategies. Last, which use the surprisal of the final word. Max, which takes the highest surprisal in the sentence. And finally, min, which averages surprisal across content words. Through these three ways, we aim to carefully test how robust the relationship between surprisal and the contradiction really is. This slide shows how different context settings change word-level surprisal, using an example from the Wikicapital dataset. In line A and B, we use the edge-only setting, where the model sees only the hypothesis. In A, the fourth statement, the capital of Malta is Brasilia, gives high surprisal on Brasilia, meaning that the model finds it unexpected. In B, the true statement, the capital of Malta is Valletta, gives very low surprisal on Valletta, since the model already knows this fact. In C, we switch to the cat setting. Here, we place the false premise before the true hypothesis. Now, the surprisal of Valletta goes up because it conflicts with the previous context. In D, we use the temp setting with a causal template, since, therefore. This makes the relationship more direct, and the surprisal of Valletta becomes even higher. This example shows our main idea clearly. When there's a semantic inconsistency, the key content word would become more surprising, and the structured context can make it stronger. Now, I want to explain why we cannot directly use token probabilities as word probabilities. There are three main problems. First, overestimation. A token can include probability for longer words that start the same way. For example, the probability of John also includes a chance of continuity Jonathan. So if we treat that token probability as the probability of the word John, we are overcounting it. Second, prefix ambiguity. Many tokens are not full words. They are only the beginning of another one. For example, the token K could lead to many names starting with letter K. So one token does not map to a single word. Third, probability mass problems. If we simply add up probabilities along different token paths, the token probability over words can become larger than 1, which should not happen. Taken together, these problems show that token probabilities do not directly give us valid word probabilities. That is why we need our token-to-word decoding method. Our token-to-word decoding algorithm has three main changes. First, constraint expansion. We only expand token sequences that can form valid word beginnings. Second, dynamic normalization. At each step, we renormalize the probability over the allowed tokens so that the total probability stays correct. Third, we add an end-of-word option. Let's make sure that a completed word gets its own probability, instead of sharing it with longer words that continue from the same prefix. Together, these steps give us a correct and accurate probability distribution over words. This example comes from the previous work. The problem is that the token for Matt shares the probability with its longer continuation, Machen. Because of this, simple token-based method gave Matt a lower surprisal than it should have. With our token-to-word decoding, we are able to separate a completed word from longer words that continue from the same prefix, so Matt and Machen receive their own probabilities. As you can see, our method correctly assigns higher surprisal to Matt than to Machen. This even works in the open vocabulary setting, as shown below. The example shows that our decoding gives valid and meaningful word-level surprisal, so as to support our following experiment. This slide shows our main empirical result. Across dataset, word-level surprisal achieved statistically significant performance in both accuracy and ROC-AUC metric. More importantly, it consistently outperforms the length baseline, as shown by the first bar in blue and the according dashed red line. The improvement held across multiple datasets, including SNI, Baby, wikivariant, and generalize across different model families such as Lemma, Gemma, and Queen. Among them, Queen performs the best of all. In short, these results show a clear positive correlation between surprisal values and contradiction labels. Here, we look more closely at why performance drops on the baby dataset and what that tells us about the model. First, correlation over causation. In the top example, the premise already says Zhang is in the bedroom, but the model still gives the low surprisal to kitchen. That is a clear contradiction. This means the model is following common word patterns instead of reasoning from the specific sentence. John is in the kitchen might be a frequent pattern in the data, so it seems likely to the model. Second, weak negation understanding. In the bottom examples, when the premise says John is not in the kitchen, the model still does not strongly increase the surprisal for kitchen in the hypothesis. In the other words, the effect of negation not is not reliably carried into the next word prediction. Thus, these examples show the existing limitations in large language models that surprisal reflects the model learned expectations. However, these expectations do not always match the correct logical reasoning. To conclude, we studied whether the word-level surprisal is linked to sentence-level contradiction in large language models. First, we introduced a token-to-word decoding method that enables us to compute accurate word-level surprisal from token-based models. That makes our work possible. Second, across multiple datasets and model families, we found a clear positive correlation between surprisal and contradiction. Third, this pattern is robust. It holds across different method variants, models, and domains. At the same time, we also identified clear limitations in existing models. They still rely heavily on common word patterns and struggle with negation understanding. It shows that the model probability distribution over the next token does not always match the correct logical reasoning. Overall, our work built a clear quantitative connection between word-level uncertainty and sentence-level semantics. We hope this helps move towards more transparent and reliable language models. Our code and data are available at the GitHub link shown here. Thank you.